candidate and alpha. And I'm glad she's giving us an overview of her recent results. And what this is also mainly about is asking for feedback from the collaborative expertise in the TRR, about how she might continue her work in the remaining month. Well, yours. Thanks for coming.
Thank you for coming and also joining the Zoom meeting. So I'm Heves, as many of you know. So I'm working in project L5, which is the project about the ocean circulation and mixing process from paleo times. And my working period is the Last Glacial Maximum, which is like 21,000 years before the present day. So here you see the difference between the present day and the LGM, which is the Last Glacial Maximum. So what we know about the Last Glacial Maximum, as you see, most of the land was covered with ice sheets. And because of this, the present day sea level was almost 130 meters was lower for the LGM conditions, as well as the global mean temperature was approximately 8 degrees Celsius colder than today. And of course, the carbon dioxide concentration was lower than the present day. So what we are looking for in this project is that because of this large ice sheet coverage, we thought that we lost almost all of our continental shelves during the LGM, and because of that, our sea level was decreased, right? So today we know that almost 70% of our tidal energy is sinking in the shelves, in this continental shelves. So if we don't have any shelves for the LGM, then what did this energy go to? This is our question. So according to LGM hypothesis, it says to us that if the continental shelves are exposed during the LGM, then this tidal energy should shift from shelves to the open ocean during the LGM. Then if we expect to see more tidal energy in the deep ocean for LGM, then we expect to see more tidal energy generation, more mixing, then maybe stronger overturning circulation at the end. So our question, or what makes our project different than the previous LGM studies, is that we are using IDEMIX mixing parameterization in our project, which is, as many of you know, an energetically consistent mixing parameterization, ocean mixing parameterization, to see if IDEMIX brings us, sorry, oh. Kind of froze. Sorry.
But just the slides, everything else is okay. Sure, what to do. Is it good? You know, the presentation mode. Sorry, I didn't. Animations don't function.
Yes, sorry for the delay. So yeah, our question is how much IDEMIX create or make difference in our mixing and overturning circulation for the LGM conditions. So I will just briefly mention about our method, like what we did in our model. So we are using ICSM model, which is the isotope-enabled community Earth system model. So it's a coupled model, global coupled model. And the default mixing parameterization for the ocean is the KPP, K-profile mixing parameterization, as you see at top there. Oh, I'm figuring out this. Okay, here. What we did is that we kept the KPP for the upper ocean and we put IDEMIX for the deep ocean. And in our method, in our strategy, we are just focusing on the mixing that is coming from the tidal internal wave breaking. So we don't have near inertial waves that can come from the mixed layer to the deep ocean and create this internal waves, also contributes to internal wave mixing. We don't have those, and we also don't have eddy parameterization for IDEMIX. So the only source to generate internal waves in our system is the tidal forcing, tidal energy that flows over the bathymetry. So here I'm just showing the difference of our bottom forcing tidal dissipation field. So now you don't see me, but this is the difference between the tidal dissipation rate between LGM and PI. This is what we use. And as you see here, in general, LGM has more tidal energy in the deep ocean at the bottom than PI, especially over the rough bathymetry, the places where we expect to see more internal wave breaking. So this was our input. And let's come to the outputs. So here we are showing the vertical diffusivity, global fields of vertical diffusivity. At top, you are seeing the cases without IDEMIX. So this is only working with KPP, K-profile parameterization. And at the bottom row, you're seeing the cases with IDEMIX. This is at 1 kilometer depth, and we are comparing the PI ocean on the left and, or depends on your left and right, and LGM on the other side. So the first thing that drags our attention is how sparse the vertical diffusivity look like when we add IDEMIX to the system. Because as you see at the top row, we kind of have this homogeneous pattern and these strange stripes over the equator, over the subtropics, and so on. So this is because in the KPP profile or in ICSM model, the vertical diffusivity, the background vertical diffusivity is constant. And they know that vertical diffusivity is a latitude dependent parameter. That's why they set a constant value for these three stripes, let's say for these three regions, based on the Coriolis force. Since the Coriolis force is 0 at the equator or really minimal, let's say, that's why they gave the smallest vertical background diffusivity for the equator band. And because it is higher for the subtropics, the Coriolis force, they gave a relatively higher number, define a relatively higher number for the subtropics. And all the rest, as you see, except some vigorous regions, they are all in the same color. Whereas with IDEMIX, with our setup, we already disabled the constant vertical background diffusivity. So the background diffusivity that we have is only coming from the IDEMIX. And that's why we have, that's why we have on some areas where we, again, over the mid-Atlantic ridge, for instance, we have more vertical diffusivity, so more mixing. And in some places where we know that actually the bathymetry is not that rough, it's actually abyssal plane, then the diffusivities are even lower. For instance, here in the present day, in this equatorial part in Pacific region, the values can get even lower than it was for the previous case. So if you look at the transects, so we can always take many transects from this global map that you see, but I'm just showing one transect along 30° west here, because I think that describes the situation the best. So it is somewhere here. Right? And here, once again, the upper row shows us the cases without IDEMIX, PI, and LGM, and here with IDEMIX, PI, and LGM. And the first thing that we see is that when we add IDEMIX to the system, it immediately maximizes the vertical diffusivity right over the top of the bathymetry, as you see. And this is a rough bathymetry. And when we get close to the deep water formation sites, for instance, here, we know that the tidal forcing was also stronger, so our bottom forcing was also stronger, then we see this impact or this increase in the vertical diffusivity, not just at the bottom, but also it goes to the upper levels. So the extent, vertical extent also gets higher. And it doesn't happen the same with everywhere, as you see. Here, it's also increased at the bottom, but it doesn't go along the way to the up till the to the surface, because probably the tidal forcing is not that strong. So, and you can still identify the equatorial band for the without IDEMIX cases in these two figures. So they almost look like the same, LGM and PI here. There are only slightly difference in this region, like near the subtropics. But that's the only difference. Yeah, so if we move on to another parameter of or output of IDEMIX, that is the turbulent kinetic energy dissipation rate. So this is what when the internal waves break, so this is the energy that comes out. And here again, I'm showing PI ocean on this column and LGM ocean on this column. So here, this is 30° west transect, and this is 120° west. So one represents the Atlantic, the other one represents the Pacific Ocean. And here what we see is that turbulent kinetic energy dissipation rate is reversely dependent on the depth. So it is reversed of, in terms of the pattern, it's reverse of vertical diffusivity. Here we are seeing this higher energy, usually at the surface. And then when it is strong, again, the tidal forcing is strong in this area, as we discussed already. We can see that this energy also penetrates towards the bottom. And of course, because of this difference, the tidal energy difference between the Pacific and the Atlantic Ocean, we usually see more vigorous ocean here on the upper row and not so in the Pacific Ocean. And here I'm just basically showing the global pattern for the same thing. This is the mean of different depth levels or depth ranges, I must say. So again, this is 1 to 2 kilometers, this is 250 to 500 meters. And once again, LGM has much higher, like, I don't know, more than 2 orders of magnitude higher dissipation rate than PI, as you see. And it is mainly at the surface comparing to the lower depths, higher depths, sorry. So I know that this looks a little scary at first because it's very colorful and there are many plots at the same time, but if you go step by step, I just wanna highlight that we are comparing the IDEMIX and without IDEMIX cases for the AMO circulation here. And as you see, when you look at the first 4 plots here, you don't recognize much differences except the Antarctic bottom water here. It got a little bit stronger for LGM, but that's the only thing we saw. First, that's why we also wanted to check the differences between these 2 cases again. This is the difference between with and without IDEMIX cases for PI and LGM. So I took the absolute values and took the difference afterwards. So this is basically showing us the increase and the difference and the decrease in the circulation. And it is a little bit strange because as you see, like they're completely the opposite. Bless you. The Antarctic bottom water gets slightly decreased for the PI ocean and slightly increased for the LGM ocean. And for the North Atlantic deep water, it's the other way around. The impact is not too much in terms of the strength, but we can see that it has a different pattern. And here I am showing the time series over our simulation year, time series for the North Atlantic deep water for the maximum strength and the Antarctic bottom water, again for the lowest, but actually the maximum strength over time. And as you see, also here for the PI ocean, it's slightly increasing for the North Atlantic deep water, so it's the upper cell, and still decreasing, maybe with a more powerful trend for LGM. For the Antarctic bottom water, it's going like in the same direction, it's increasing. No, sorry, this is the opposite sign. So it's slightly decreasing for PI and increasing for LGM because these are just the sign of the circulation. So 6 is more than 4. So what could be the result? I mean, what might cause this result? If we think about it, actually makes sense if we see this Antarctic bottom water got stronger with IDEMIX, whether it is too much or less than we expected, because we know that LGM tidal forcing is stronger than PI, and IDEMIX only works with the tidal forcing. So if we provide a stronger input, then you may expect to see more stronger circulation over here. But then why it decreased for the PI? We may say that because when you remove the constant vertical and artificial vertical background diffusivities and so on, and just depend on the tidal forcing for the present day, so you may also expect to see some decrease. And for the North Atlantic deep water, it's not exactly the same because it might be on different reasons, actually. We know that buoyancy becomes more important for the upper ocean, and of course, based on that stratification and so on. So, but what we may say is that for the LGM ocean, at least, the lower or the weaker and shallower North Atlantic deep water over here is a good thing, because that's also what we know from the proxy data, that LGM most probably had weaker and shallower North Atlantic deep water. For the Antarctic bottom water, on the other hand, is a mystery. According to some proxies, we expect to see stronger and also deeper Antarctic bottom water, and for some of the other references, we may say that it might be the same as the present day. But this might be the few comments about these plots.
Can I ask a question in between?
Of course. Oh, sorry.
So isn't that kind of very surprising? For example, just look at the AMO just with IDEMIX. So you, in the previous slide, you said that the vertical mixing is increased by a factor of 10 or something, but the AMO is decreasing.
Exactly. That is the ultimate questions that we want to find an answer to, because it was also kind of shocking for us to observe. Like, we like the result in terms of the LGM, because at least it didn't, because North Atlantic deep water was already shallower and weaker without IDEMIX. When we add IDEMIX on top of it, it got even stronger in terms of the weakening and so on. So in terms of that, we are happy with the impact of IDEMIX, but why it decreased more with the stronger tidal forcing? Yes, it's a mystery. And that's kind of where I need more feedback, because I need to look into more parameters. I need to do more analysis to understand, okay, maybe there's a compensating mechanism that kind of like eliminates the actual impact of IDEMIX. Yeah. So as I mentioned, this is actually to represent the same thing. like, I just wanted to check how the stratification change between PI and LGM ocean. Again, I'm showing the differences. This is again one transect along 30° west. And one thing that grabbed my attention was that how the stratification gets stronger here, where we know that deep water formation happens for the North Atlantic deep water. And this might be one of the reasons, at least, that we can correlate why the North Atlantic deep water got weaker and shallower, because what I saw from the other references and so on, I learned that for the upper ocean, and we already knew it actually, the buoyancy flux, so as the stratification, it's the one of the major drivers for the convection, whereas for the deep ocean, tidal mixing becomes more important or maybe more dominant than stratification based on the location, based on the depth and so on, yes, but at least for this case, for the North Atlantic deep water, we can say that for the upper oceans, stratification might be a important factor. Like this might be the result of IDEMIX on it. So this is the last complicated plot that I'm not going to try to explain it because I'm also trying to understand. This is just showing another difference between with and without IDEMIX cases, this time the Southern Ocean, meridional overturning circulation. And as you see, like it looks completely a mess in terms of the differences. Like there are many water masses, water bodies in the Southern Ocean, as we all know. And I'm just curious, like why we have this decrease in the upwelling in this Deacon near or in the Deacon cell, for instance. So that's why at this point, and even further this, I need more feedback from you guys because I know something is going on here, and as it's already mentioned that we have, these are our questions, like, okay, to what extent does IDEMIX impact the ocean mixing and the circulation? And we kind of show those impacts already in our plots. Now, the second question comes, why this impact is so minimal, especially when we have larger LGM tides? So in order to answer these questions, I need more analysis than these. And probably for the Southern Ocean, when we look at these different values here, of course, once again, they're not too much, they're not stronger, but probably I need to check the wind surface, wind stress in the Southern Ocean. I need to check for the buoyancy flux. Basically, the sea and air interaction for both Southern Ocean and the North Atlantic, which I'm going to do soon. And but I also need to know, I guess, that's also one of the suggestions from Frederica, how the water masses change between with and without IDEMIX cases. So how the water mass transformation happened between these two cases. And yeah, I may use some expertise in that sense. Unfortunately, this is all I can say at the moment to you, because I'm also curious about what will come next. But yeah, this is why we are having this talk today, so thank you.
How do you compute the MOC in the Southern Ocean? Is that with the impact of things?